In the 18th century, chemistry was not yet the precise science we recognize today. It was a field filled with observations, experiments, and scattered ideas, but lacking a clear and unified framework. Substances could be mixed, heated, and transformed, yet the underlying principles behind these changes were poorly understood. One of the dominant theories at the time, known as the phlogiston theory, claimed that a substance called phlogiston was released during burning. This idea shaped how scientists interpreted chemical reactions, even though it could not fully explain what was actually happening. It was within this uncertain and often confusing scientific landscape that Antoine Lavoisier began his work. Antoine Lavoisier was born in 1743 in Paris, into a wealthy family that provided him with access to education and resources. From an early age, he showed an interest in science, but his path was not limited to a single discipline. He studied law as well as natural philosophy, reflecting the broader intellectual culture of the time, where scientific inquiry was often combined with other fields of study. Despite his legal training, Lavoisier's true focus became science. He was drawn to experimentation, particularly in chemistry, where he saw the potential to bring order and clarity to a field that lacked consistency. Unlike many of his contemporaries, who relied heavily on qualitative observations, Lavoisier emphasized precise measurement. He believed that understanding chemical processes required careful quantification, weighing substances before and after reactions to determine exactly what was happening. This approach would become one of his defining contributions. At the time, many experiments were conducted without strict attention to measurement, leading to interpretations that were often incomplete or incorrect. Lavoisier introduced a level of rigor that transformed how chemistry was practiced. By using accurate balances and controlled conditions, he was able to track changes in mass and identify patterns that others had overlooked. One of the key problems he addressed was combustion. According to the phlogiston theory, when a substance burned, it released phlogiston into the air, leaving behind a residue. However, this explanation had inconsistencies. In some cases, materials appeared to gain weight after burning, which did not fit the idea of losing a substance. Lavoisier recognized that something in this theory was fundamentally flawed. Through a series of carefully designed experiments, he began to uncover the true nature of combustion. He found that when substances burn, they combine with a component of the air rather than releasing something into it. This component, which he later named oxygen, plays a central role in combustion. When a material burns, it reacts with oxygen, forming new compounds and often increasing in mass due to the addition of this element. This was a critical shift. Instead of viewing combustion as a process of loss, Lavoisier showed that it is a process of combination. This insight overturned the phlogiston theory, replacing it with a more accurate understanding of chemical reactions. It marked the beginning of modern chemistry, where reactions are seen as interactions between substances rather than mysterious transformations. Lavoisier's work extended beyond combustion. He studied respiration, showing that the process by which living organisms use oxygen is similar to combustion. In both cases, oxygen is consumed and energy is released. This connection linked chemistry with biology, demonstrating that the same principles apply to both living and non-living systems. He also played a central role in redefining the concept of elements. At the time, the list of known elements was unclear and often included substances that were not truly fundamental. Lavoisier introduced a more systematic approach, identifying elements as substances that cannot be broken down into simpler components by chemical means. He compiled a list of elements based on experimental evidence, helping to bring clarity to the field. Equally important was his work on chemical nomenclature. Before Lavoisier, the naming of substances was inconsistent and often confusing. Different scientists used different terms, making communication difficult. Lavoisier, along with his collaborators, developed a standardized system of naming chemicals based on their composition. This system made it easier to describe reactions and share knowledge, contributing to the growth of chemistry as a coherent science. Underlying all of these contributions was a single principle that would become central to modern chemistry: the law of conservation of mass. Through his precise measurements, Lavoisier demonstrated that in any chemical reaction, the total mass of the substances involved remains constant. Matter is not created or destroyed, but transformed. This principle provided a solid foundation for understanding chemical processes, allowing scientists to analyze reactions with greater confidence and accuracy. What made Lavoisier's work especially powerful was its clarity. He did not rely on vague concepts or assumptions. Instead, he used careful experiments and precise measurements to reveal the underlying structure of chemical reactions. His approach turned chemistry into a quantitative science, where results could be tested, verified, and reproduced. By the time his early work had matured, the field of chemistry had already begun to change. The phlogiston theory was losing its hold, replaced by a new understanding based on oxygen and measurable interactions. The concept of elements was becoming clearer, and the language used to describe chemical processes was becoming more consistent. Antoine Lavoisier had not simply added new knowledge to chemistry. He had redefined its foundation, and in doing so, he set the stage for a transformation that would shape science for centuries to come. As Antoine Lavoisier's ideas began to take hold, the transformation of chemistry accelerated. What had once been a fragmented discipline, filled with competing theories and unclear terminology, started to develop into a structured and coherent science. This shift did not happen instantly or without resistance. The phlogiston theory had been widely accepted for decades, and many scientists were reluctant to abandon it. Yet Lavoisier's evidence was precise, repeatable, and increasingly difficult to ignore. His approach was fundamentally different from what had come before. Where earlier chemists often relied on observation alone, Lavoisier insisted on measurement. He used carefully calibrated balances to weigh substances before and after reactions, tracking even the smallest changes. This allowed him to demonstrate with clarity that mass is conserved in chemical processes. When something appeared to be lost, it had in fact combined with a gas or transformed into another form that could be measured. This insistence on precision reshaped experimental practice. Chemistry was no longer about what seemed to happen. It became about what could be proven through consistent and measurable results. Lavoisier's laboratory became a model of this new method, where experiments were designed not only to observe reactions, but to quantify them in detail. One of the areas where this approach had a major impact was the study of gases. At the time, gases were poorly understood. They were often treated as secondary substances, difficult to measure and analyze. Lavoisier changed this by incorporating gases into his experiments with the same level of precision as solids and liquids. He designed apparatus that allowed him to capture, measure, and study gases produced during reactions. Through these experiments, he was able to identify and characterize several important gases. He confirmed the role of oxygen in combustion and respiration, showing that it is consumed during these processes. He also studied hydrogen, which when combined with oxygen produces water. This finding led to another important conclusion. Water, previously thought to be an element, was actually a compound made of two simpler substances. This realization had far-reaching consequences. It meant that substances long considered fundamental could be broken down into simpler components. The definition of an element had to be revised, and chemistry moved closer to a systematic understanding of matter. Lavoisier's list of elements, though not complete by modern standards, represented a major step toward clarity and organization. At the same time, his work on chemical reactions became more detailed. He demonstrated that acids, for example, often contain oxygen, leading him to propose that oxygen was a defining component of acidity. Although this idea was later refined, it showed his attempt to identify underlying patterns in chemical behavior. He was not satisfied with isolated facts. He sought general principles that could explain multiple observations. Lavoisier also collaborated closely with other scientists. Chemistry was becoming increasingly complex, and progress required the exchange of ideas and methods. He worked with colleagues such as Pierre Simon Laplace, applying chemical principles to broader questions. Together, they conducted experiments on heat and respiration, using calorimeters to measure the heat produced by living organisms. These experiments revealed a deep connection between chemistry and life. They showed that respiration in animals is essentially a slow form of combustion, where oxygen reacts with substances in the body to release energy. This insight linked biological processes to chemical principles, reinforcing the idea that the same laws govern both living and non-living systems. Another major contribution during this period was the reform of chemical language. Before Lavoisier, chemical names were inconsistent and often based on tradition rather than logic. This made it difficult for scientists to communicate clearly. Lavoisier and his collaborators introduced a new system of nomenclature based on composition and structure. Substances were named according to the elements they contained and the proportions in which they combined. This system brought order to chemistry. It allowed scientists to describe reactions in a consistent way, making it easier to share knowledge and build on each other's work. The new nomenclature also reflected Lavoisier's broader philosophy that science should be clear, precise, and grounded in observable reality. His work was brought together in his major publication, Traité élémentaire de chimie, published in 1789. This book is often considered the first modern textbook of chemistry. It presented the principles of the new chemistry in a systematic way, including the law of conservation of mass, the role of oxygen, and the revised list of elements. It also included detailed descriptions of experiments and apparatus, making it a practical as well as theoretical guide. The impact of this publication was significant. It provided a clear and comprehensive framework that others could follow. Students and researchers now had a reference that organized chemical knowledge into a coherent system. The ideas that had been developed through individual experiments were now presented as part of a unified theory. Despite this progress, Lavoisier's work did not go unchallenged. Supporters of the phlogiston theory continued to defend their views, and debates within the scientific community were often intense. However, as more experiments confirmed Lavoisier's findings, the balance began to shift. The weight of evidence increasingly favored the new chemistry, leading to a gradual but decisive change in scientific thinking. Beyond his scientific work, Lavoisier was also involved in public and administrative roles. He contributed to projects related to agriculture, finance, and public policy, reflecting the broader role that scientists often played in society at the time. He worked on improving agricultural practices, studying soil composition and crop yields. He also participated in efforts to reform taxation and economic systems. These activities showed another aspect of his thinking. He believed that scientific knowledge could be applied to practical problems, improving efficiency and benefiting society. This connection between theory and application was consistent with his approach to chemistry, where understanding was always linked to measurable results. By the end of this period, the transformation of chemistry was well underway. The old framework, based on phlogiston and qualitative observation, was being replaced by a new system grounded in measurement, clear definitions, and consistent language. Chemical reactions were no longer mysterious processes, but interactions that could be analyzed and understood in detail. Antoine Lavoisier stood at the center of this transformation. Through careful experimentation, logical reasoning, and a commitment to clarity, he had redefined the field. His work did not simply add new information. It changed how chemistry was practiced, turning it into a science that could build systematically on its own foundations. And as this new framework spread, it began to shape not only chemistry, but the broader scientific understanding of matter itself. As Antoine Lavoisier's scientific influence reached its peak, the transformation of chemistry was no longer a gradual shift, but a decisive turning point. The old framework built on phlogiston theory was steadily collapsing under the weight of precise measurement and repeatable evidence. In its place, a new chemistry was emerging, one that treated matter as something that could be defined, measured, and systematically understood. Yet while his scientific legacy was becoming stronger, The world around him was moving in a direction that would place his life in increasing danger. The late 18th century in France was not only a time of intellectual progress, but also of political instability. The French Revolution began to reshape every aspect of society, including institutions, professions, and individuals who were associated with the old order. Lavoisier, despite being a scientist, was not isolated from these changes. His role extended beyond a laboratory into areas that would later become controversial. He was involved in the Ferme Générale, a private organization responsible for collecting taxes on behalf of the government. At the time, this position provided him with financial resources that supported his scientific work. It allowed him to build a well-equipped laboratory, acquire instruments, and conduct experiments with a level of precision that few others could match. However, during the Revolution, tax collectors became symbols of inequality and exploitation, regardless of their individual contributions to society. This association would prove dangerous. While Lavoisier continued his scientific work, contributing to the advancement of chemistry, the political climate grew increasingly hostile. Revolutionary leaders were focused on dismantling the structures of the old regime, and individuals connected to those structures were often viewed with suspicion. Despite these tensions, Lavoisier remained active in science and public service. He contributed to national projects, including efforts to standardize weights and measures. This work would later lead to the development of the metric system, a universal and consistent method of measurement that reflected the same principles of precision and clarity he had applied to chemistry. His involvement in such initiatives demonstrated his belief that science could serve society in practical and lasting ways. At the same time, his scientific work continued to influence the field. The principles he had established were being adopted by other chemists across Europe. Laboratories began to follow his methods, using precise measurements and standardized terminology. The new chemistry was spreading, becoming the dominant framework for understanding matter and reactions. Yet the political situation in France was becoming more unstable. The revolution intensified, leading to a period known as the Reign of Terror. During this time, many individuals were arrested and executed based on their perceived connections to the old system. Scientific achievements offered little protection against political accusations. In 1794, Lavoisier was arrested. The charges against him were not related to his scientific work, but to his involvement in tax collection. Despite his contributions to science and his efforts to improve society through knowledge, he was judged within the context of the political environment rather than his intellectual achievements. His trial was swift. There was little consideration of his scientific importance, and appeals on his behalf were unsuccessful. One of the most well-known statements associated with this moment reflects the attitude of the time, that the Republic had no need of scientists. Whether spoken exactly in that form or not, it captures the reality that intellectual contributions were overshadowed by political priorities. Lavoisier was executed by guillotine in May 1794. His death marked a sudden and tragic end to a life that had transformed an entire field of science. Within a short period, one of the most important figures in chemistry had been removed, not because of his work, but because of the political forces surrounding him. The impact of his loss was immediately recognized by the scientific community. Many understood that his execution was not only a personal tragedy, but also a loss for knowledge and progress. His work, however, could not be undone. The principles he had established were already embedded in the practice of chemistry, continuing to guide research and discovery. In the years that followed, the significance of Lavoisier's contributions became even clearer. The new chemistry he had developed provided a foundation for future advances. Scientists built on his ideas, refining the understanding of elements, compounds, and reactions. The law of conservation of mass became a central principle, and the systematic approach he introduced remained a core part of scientific methodology. His work also influenced how science itself was perceived. He demonstrated that progress depends not only on ideas, but on methods. Precision, measurement, and clear communication became essential components of scientific practice. These principles extended beyond chemistry into other fields, shaping the broader development of modern science. Lavoisier's life illustrates a powerful contrast. On one hand, he represents clarity, logic, and the pursuit of knowledge through careful reasoning. On the other, his death reflects the unpredictability of historical events, where intellectual achievement does not always protect against external forces. Yet even in this contrast, his legacy remains strong. The system he created did not disappear with him. It continued to grow, influencing generations of scientists and shaping the way matter is understood. His work marked the transition from an uncertain and fragmented field to a structured and reliable science. By the end of the 18th century, chemistry had been fundamentally redefined. The language, methods, and principles introduced by Lavoisier had become the new standard. What had once been a collection of ideas was now a discipline with clear foundations and the ability to progress systematically. And at the center of that transformation was Antoine Lavoisier, whose work endured even as the circumstances of his life came to a sudden and tragic end. In the years following Antoine Lavoisier's death, the full scale of his impact began to unfold with a clarity that had not been fully visible during his lifetime. What he had introduced was not just a set of discoveries, but a complete restructuring of chemistry as a discipline. His methods, his language, and his principles became the framework through which future scientists would understand matter, reactions, and transformation. Even though his life had ended abruptly, his work continued to expand, influencing developments far beyond what he could have directly imagined. The most immediate effect of his legacy was the complete disappearance of the phlogiston theory. Within a relatively short time after his death, the older framework that had dominated chemistry for decades was abandoned. The evidence Lavoisier had provided was too precise, too consistent, and too repeatable to ignore. Combustion was no longer explained as the release of an invisible substance, but as a reaction with oxygen. This shift may seem simple in retrospect, but it represented a fundamental change in how scientists approached explanation itself. Instead of relying on assumptions, chemistry now depended on measurable proof. This change influenced every area of the field. Reactions were analyzed through mass balance, ensuring that all substances involved were accounted for. Experiments were designed with control and precision, reducing ambiguity and increasing reliability. Lavoisier had effectively introduced a new standard for what counted as scientific evidence. His influence also shaped the development of atomic theory. Although Lavoisier himself did not formulate the modern concept of atoms as we understand it today, his definition of elements as substances that cannot be broken down laid the groundwork for later scientists. John Dalton, for example, would build on these ideas in the early 19th century, proposing that elements are made of indivisible atoms that combine in fixed ratios to form compounds. This progression shows how Lavoisier's work acted as a bridge. He moved chemistry from a state of confusion into one of clarity, making it possible for more detailed theories to emerge. Without a clear definition of elements and compounds, atomic theory would have lacked a stable foundation. His contribution was not the final answer, but the essential step that made further answers possible. Another area where his impact became increasingly visible was chemical analysis. The techniques he developed for measuring and tracking substances evolved into more advanced methods, allowing scientists to identify the composition of complex materials. This capability became crucial for industries such as medicine, agriculture, and manufacturing. The ability to understand what substances are made of and how they react opened the door to control production and innovation. His work on nomenclature continued to play a central role as well. The system of naming chemicals based on their composition allowed scientists from different regions to communicate clearly and consistently. This might appear to be a simple administrative improvement, but in reality, it was essential for the growth of science. Without a shared language, collaboration becomes difficult and progress slows. Lavoisier's system provided the clarity needed for chemistry to develop as a global discipline. As the 19th century progressed, the influence of his ideas extended into education. Chemistry began to be taught as a structured subject, with clear principles and standardized terminology. Textbooks were written using the framework he had established, and students learned to approach experiments with precision and logical reasoning. This educational shift ensured that his methods would be carried forward by future generations. At the same time, his work began to influence other scientific fields. The emphasis on measurement and conservation principles found applications in physics, particularly in the study of energy and thermodynamics. The idea that quantities are conserved during transformations became a unifying concept across disciplines. Lavoisier's law of conservation of mass would later connect with the broader principle of conservation of energy, forming part of a larger framework for understanding physical processes. His contributions also had practical consequences beyond the laboratory. In agriculture, for example, understanding the chemical composition of soil and fertilizers allowed for more effective farming methods. In medicine, knowledge of chemical reactions contributed to the development of treatments and pharmaceuticals. In industry, the ability to control chemical processes led to more efficient production of materials. These applications reflect an important aspect of Lavoisier's legacy. He did not separate theory from practice. His work showed that understanding the fundamental nature of matter has direct consequences for everyday life. By bringing clarity to chemistry, he made it possible to apply that knowledge in ways that improve efficiency, productivity, and health. Despite these advances, the story of Lavoisier remained marked by its abrupt ending. The contrast between his intellectual achievements and the circumstances of his death continued to resonate. It served as a reminder that scientific progress does not occur in isolation, but within a broader social and political context. The same society that benefits from knowledge can also, at times, fail to recognize its value. Yet the persistence of his ideas demonstrates something equally important. Knowledge, once established through clear evidence and reasoning, has a durability that extends beyond individual lives. Lavoisier's principles did not disappear with him. They continued to spread, to be taught, and to be refined. His work became part of the foundation upon which modern chemistry was built. By the time the scientific world moved deeper into the 19th century, the transformation he had begun was complete. Chemistry was no longer a collection of isolated observations. It had become a systematic science, capable of explaining and predicting the behavior of matter with increasing accuracy. The methods he introduced, the language he created, and the principles he established were now standard practice. And although his life had ended in a moment shaped by political forces, the intellectual structure he built remained intact, continuing to support the growth of science long after he was gone. As the centuries moved forward, the true scale of Antoine Lavoisier's impact became impossible to overlook. What he had built in the late 18th century did not remain confined to his time. It expanded, adapted, and became the backbone of modern science. The clarity he brought to chemistry continued to ripple outward, shaping not only how scientists study matter, but how entire industries function and how modern life itself is structured. By the time the 20th and 21st centuries emerged, chemistry had evolved into one of the most powerful tools humanity possesses. From pharmaceuticals to energy systems, from agriculture to advanced materials, nearly every major technological advancement relies on the ability to understand and control chemical reactions. And at the core of that ability lies the framework Lavoisier established, the insistence that reactions must be measured, that substances must be clearly defined, and that transformations must obey consistent laws. The law of conservation of mass, which he demonstrated with such precision, remains one of the most fundamental principles in science. Even as physics later expanded this idea into broader conservation laws involving energy and matter, the foundation remained the same. Nothing simply disappears. It changes form. This principle allows scientists to track reactions, design processes, and ensure that systems behave as expected. It is a quiet rule, but it governs everything from simple chemical reaction in a laboratory to large-scale industrial production. In modern chemistry, Lavoisier's influence is so deeply embedded that it often goes unnoticed. Students learn to balance equations, to measure substances, and to classify elements without realizing that these practices were once revolutionary. The structure of the periodic table, the understanding of compounds, and the precise language used to describe reactions all reflect the shift he initiated. Chemistry is no longer uncertain or descriptive. It is predictive, controlled, and exact. This transformation has made possible entire fields that define contemporary life. The development of medicines depends on understanding how molecules interact within the body, how reactions can be controlled to produce desired effects, and how substances can be synthesized with precision. The production of materials, from plastics to advanced alloys, relies on the ability to manipulate chemical structures in predictable ways. Even environmental science depends on chemical analysis to understand pollution, climate processes, and ecological balance. All of these advancements trace back, in part, to the clarity Lavoisier introduced. He turned chemistry into a language that could be used reliably, a system where knowledge could accumulate rather than remain fragmented. This ability to build on previous work is what allows science to progress over time, moving from simple observations to complex systems of understanding. At the same time, his story continues to carry a deeper message about the relationship between knowledge and society. Lavoisier lived at a moment when scientific progress and political upheaval collided. His contributions were immense, yet they did not protect him from the forces of his time. This contrast remains relevant, reminding us that the value of knowledge is not always recognized in the moment, and that progress can exist alongside instability. Yet there is also a sense in which his work transcended those circumstances. While his life ended abruptly, the system he created proved stronger than the events that surrounded him. It continued to grow, to be adopted across nations, and to shape the direction of science long after the political environment that ended his life had changed. This endurance reflects a fundamental aspect of knowledge, that once it is grounded in evidence and clarity, it can persist beyond individual lives and historical moments. In many ways, Lavoisier represents a turning point not just in chemistry, but in how science itself is practiced. He showed that progress requires more than ideas. It requires method, discipline, and a commitment to precision. It requires a willingness to question existing theories, but also the ability to replace them with something more reliable. His work demonstrated that science advances when observation is combined with measurement, when language is standardized, and when results can be reproduced and verified. This approach has become the standard across all scientific disciplines. Whether in physics, biology, or engineering, the principles of careful measurement and clear definition remain central. They allow scientists to communicate, to test ideas, and to build systems that function consistently. Lavoisier's influence extends into all of these areas, not through specific discoveries alone, but through the structure he gave to scientific thinking. Looking at the modern world, it becomes clear how deeply this structure is embedded. The technologies that define daily life, from energy systems to medical treatments, depend on controlled chemical processes. The ability to produce, transform, and analyze substances is fundamental to modern society. These capabilities did not emerge suddenly. They developed over time, built on a foundation that Lavoisier helped create. Even the way we think about matter has changed because of him. Substances are no longer mysterious or undefined. They are composed of elements, combined in specific ways, following predictable rules. Reactions are not arbitrary. They are governed by principles that can be understood, measured, and applied. This shift from mystery to clarity is one of the most significant changes in the history of science. In the end, Antoine Lavoisier's legacy is not just found in textbooks or laboratories. It is present in the structure of modern knowledge itself. He took a field that was uncertain and gave it order. He replaced assumption with evidence, confusion with clarity, and inconsistency with system. Through this transformation, he made it possible for chemistry to become a true science, one capable of continuous growth and application. And in doing so, he did something that extends far beyond his own time. He changed the way humanity understands matter, not as something mysterious and unpredictable, but as something that can be studied, measured, and ultimately understood. That shift, once made, continues to guide science forward, shaping the way we explore the world and the way we use what we discover.